Alright, welcome back to the second of these little talks on the physiology of the endocrine system. And as in the first talk, we had a little preamble talking about both polar and non-polar hormones and their actions on target cells. So now we've discussed what happens with the non-polar hormones, which includes the steroid hormones plus one other type, which is the thyroxine or T4 hormone released by the thyroid. We can now turn our attention to the polar hormones, which is basically all the other hormones, and how they act. Now, again, the key point is the amount of charge on the chemical messenger or hormone itself dictates what it can do at the target cell. So, as you learned earlier on in the course, things with large amounts of charge and large size cannot pass through a phospholipid bilayer of any cell. And this is the case for the polar hormones. They cannot pass the cell. So they have to stimulate a change in the cell by doing so in a slightly different manner. And the analogy I always use for this particular process is the same as you would say use for taking a message back to your own house or taking a message around to a neighbour's house who you don't know very well. In the first scenario, we looked at the steroid hormones and T4 hormone, and that's the analogy with living in your own house. You get, some good news. Say you've gone and got a scratch card and you've won, say $10,000 on your scratch card at the shop. So then you head home. So this is the same as the non-polar hormone, getting in the car, driving home, the car being the protein transporter. You arrive, you park your car in the garage, which is the protein transporter dropping off the steroid hormone or the T4, which is you. You get out of the garage and your house is your cell, and so you go straight through the front door and straight into the house and stay straight upstairs to the bedroom where your partner happens to be doing something, and you give them the good news, you've just won 10,000. And so, after lots of hugging and jumping up and down and shrieking, you both go off and create a change, like, buy a new car, for example. So that analogy fits closely with what happens when a steroid hormone stimulates a target cell. It needs help, traveling toward the cell through the bloodstream, and once it gets there, it can pass through the cell membrane, which in this case is the doorway of the house. Now, I didn't add an analogy for inside the house moving from the cell membrane to the nuclear membrane, but that could be, say, you need to use the stairs to get up to the second floor, for example, and then that's where the nucleus is, and that's where you have the message given over. But the message is carried by the same carrier all from the start to the finish. So when you tell your partner you won the $10,000, it's you doing it. It's not, you haven't had to pass it down between other people. So hopefully that analogy works for you on some level. If not, dump it and just carry on with what we said before. So in this particular instance, we're now going to look at polar hormones, and as I said, because they have charge, they can't go into the house, they can't enter the cell. So in this analogy, you're carrying a message. Say someone got hurt at work and they're a relative of the person who lives down the street from you who doesn't, for whatever reason, have a phone. So you just walk down the street. You don't need a transporter because you interact with the environment, it's close enough. You get to their house, but you don't just walk in the front door. You stand outside the door and you ring the bell and you wait. And this is what polar hormones have to do. They have to wait outside. They cannot enter the house. And in this case, the person that you want to give the messenger to, for example, say it's the mother of the household, isn't actually the one that comes to the door. Say it's her son, who's about 10 years old, that comes to the door and has been trained not to open the door to strangers, and so it just kind of shouts through the door, "What is it?" And then you have to relay your message by shouting the message through the door, and then the little boy will take that message up to another part of the house and give it to his mother, who will then, obviously probably head straight to the hospital, etc. and so you've had your message transferred. And that is basically the analogy for how polar hormones get their job done. They're the first messenger, but they can't get the message by themselves all the way to the point where the change is made inside the cell. Instead, they have to pass the message on to another chemical, which becomes known as the secondary messenger, because it's the second molecule to carry that message on, which will eventually result in a change inside the cell. So in this analogy, the secondary messenger was the little boy who stood on the other side of the door. So let's actually look at the diagram now and talk through how it's different from steroid hormone, because just like it's a classic to say compare and contrast steroid hormone and T4 on a target cell, excuse me, it's equally valid to get you to compare and contrast how a non-polar hormone stimulates a target cell versus a steroid hormone. So these are non-polar hormones. Sorry, haha. I was just thinking about steroid. Well, there's a mistake for you. Polar hormones with charge on them. Okay, so here's our blood vessel. So the blood is flowing this way. Here's our capillary with spaces in it for things to come out. The polar hormone is traveling through the blood. Here's one here, and it's come out. And it makes its way down, and it attaches on to a receptor. And that's the first difference. There's a receptor in the cell membrane for polar hormones. So it binds, this receptor is a G protein, and it's called a G protein because it sort of holds the G shape, capital G shape, with its tail there. So G protein, and when it binds there, this protein slightly changes its shape, and there's an alpha, beta, gamma subunit gets pushed off. The alpha, beta, gamma subunit is fat soluble, so it sits within the phospholipid bilayer, and it stays inside there, it doesn't move out, and it attaches here. When it does that, it attaches onto a protein sitting in the membrane. Now I'm going to go through two different protein that it attaches to, two different ways the secondary messenger is stimulated. And the first protein sitting in the membrane is called adenylate cyclase. Now enzymes always are named for what they do. Now first, you know it's an enzyme because it finishes in ASE, A's. Anything finishes in A's is an enzyme, means it catalyzes a reaction. So it catalyzes the reaction of adenylate or adenosine triphosphate. So ATP is very, very well distributed throughout the cell. It's abundant. So it takes an ATP molecule. When it's stimulated by this binding here, it activates the adenylate cyclase, and it cleaves the ATP into AMP, so it moves two phosphate molecules off. So if we draw that out, then you've got your there's your adenosine sugar and then your three phosphates, and what it does is it basically separates it there, so you've got AMP monophosphate and two PIs. Now that just goes off and gets into other biochemical reactions. We're interested in this thing here, the CAMP or cyclic AMP, because this is the secondary messenger. So our original polar hormone, which could have been epinephrine, is released. It binds a G protein. alpha beta subunit moves off, stimulates the protein next down the chain, which is adenylate cyclase. This cleaves ATP to cyclic AMP. We've created our secondary messenger, which is basically going to create phosphorylation reactions inside the cell. Now we're at a stage in our learning where phosphorylation reactions and all those biochemical cascades are new to us, so we don't need to understand them. We just need to understand the mechanism of how that gets triggered to happen. So we get to cyclic AMP, we've created our secondary messenger, changes in the cell take place, job done. So that is adenylate cyclase. Now what I want to do is show you another one. So this time, this protein will be known as phospholipase C. So exactly the same thing happens here, but phospholipase, as I said, remember A's tells you it's an enzyme, and the first part tells you what it affects. Well, phospholipase affects phospholipids. And if you remember, phospholipids is what the membrane is made up of. So what phospholipase C does when it's stimulated to do so is it takes a phospholipid and it breaks it into two parts. DAG, IP3. Ooh. Now, DAG is something we would look at a higher level of physiology, and it's very important and does a lot of things, but for us right now it's just a byproduct. We're interested in this here because this molecule diffuses across the cytoplasm to this thing here, which is the smooth ER, and the smooth ER is full of calcium ions. And that causes the opening of gates and calcium is released. The calcium causes a biochemical cascade and you get your changes in your cell. This is your secondary messenger. So the phosphase lipase C reaction splits a phospholipid into these two. This is your secondary messenger, which causes calcium release, which bounds onto something called a calmodulin, which then activates a protein kinase and phosphorylation reactions take place. That part is nice if you understand it, but you don't have to have it at this level. So in a polar hormone, released from the blood, doesn't require any transport because it's charged, arrives when it binds on the G protein receptor. This is a receptor, remember? And it will only affect cells that have that particular receptor in it. So it's specific. Once it's bound, it causes a conformational change in the protein because the charge changes or influences the protein shape. That knocks off the alpha beta subunit and it stimulates the enzyme bedded into the wall further downstream, which could be either an adenylate cyclase or it could be a phospholipase C. If it's adenylate cyclase, ATP is cleaved to cyclic AMP, which is your secondary messenger, and that's your job done. In the case of phospholipase C, it splits a phospholipid into IP3 and DAG. IP3 releases calcium from the smooth endoplasmic reticulum. Job done. Okay, so that's how a polar hormone stimulates a change in the target cell. This whole process is known as a, let's see where we can put this. Signal transduction. It's an important concept in physiology, and particularly in endocrinology. Signal transduction is where your original messenger causes a change or biochemical cascade inside its target cell, which brings on new activity within the cell. Alright, so I've already said the main questions you can get asked. You can be asked to compare a non-polar steroid hormone against a non-polar T4 hormone. So you're looking, for how they act in the two changes in the T4, which is cleaved to T3 in the cytoplasm, and uses a different uses retinoic acid as its partner on the half sites on the DNA. You could be asked to compare and contrast a steroid hormone action on a cell with a polar hormone. So one comes through and steroid hormone acts on the DNA directly, and the polar causes a signal transduction by a binding to a receptor site, which is a G protein on the outside of the cell, and creates a secondary messenger inside the cell. And finally, I could ask you to compare and contrast how a signal transduction takes place using phospholipase C or adenylate cyclase. So in phospholipase C, a phospholipid is broken into two parts. The IP3 then causes release of calcium from the smooth endoplasmic reticulum, cascade takes place. Adenylate cyclase causes the breaking of ATP into cyclic AMP and diphosphate. And your cyclic AMP then causes the secondary messenger, then causes the cascade of responses. And that's it for the key parts or the key concepts within the endocrine physiology. So thank you for listening.